A rock in space, 400,000 kilometers from every sunset and sunrise on Earth, should have no business turning red. It has no atmosphere, no dawn, no dusk. And yet, every year or two, the full moon slides into our planet's shadow and glows like a dying coal instead of vanishing into black. The moon is not producing light. It is stealing it, secondhand, from us. Start with the basic setup. A lunar eclipse happens when Earth passes directly between the sun and the moon, casting its shadow outward into space. That shadow has two parts. The outer region, the penumbra, is a zone of partial shade, where sunlight is dimmed but not blocked. The inner region, the umbra, is the deep shadow, where Earth blocks the sun's disk completely. Earth is about 12,742 kilometers wide, roughly 3.5 times the moon's diameter, so its shadow is enormous, easily large enough to swallow the moon whole. If Earth had no atmosphere, that is exactly what would happen. The moon would go black, disappearing from the sky like a light switched off. But Earth does have an atmosphere, a thin shell of gas only about 100 kilometers thick, and that thin shell changes everything. Sunlight doesn't just stop at Earth's edge. It grazes the rim of the planet and bends. This is refraction, the same effect that makes a straw look bent in a glass of water. Earth's atmosphere acts like a lens wrapped around the whole planet, bending sunlight inward, funneling a portion of it into the umbra, into the very shadow that should be empty. So during a total lunar eclipse, the moon isn't sitting in true darkness. It's being lit by sunlight that has been redirected around the curve of the Earth, arriving from every sunrise and every sunset happening on the planet at that exact moment. Now here's where the color comes in, and it's the same physics that paints our own skies at dawn and dusk. Sunlight looks white, but it's a mixture of every color, each with a different wavelength. When that light enters Earth's atmosphere, it collides with molecules of nitrogen and oxygen. Shorter wavelengths, blues and violets, scatter easily off these tiny molecules, a phenomenon called Rayleigh scattering. Longer wavelengths, reds and oranges, scatter far less and punch through more directly. That's why our sky is blue during the day, blue light bouncing everywhere, and why sunsets turn orange and red, because at a low angle, sunlight travels through more atmosphere, and most of the blue gets scattered away before it reaches your eyes, leaving the red and orange behind. During a lunar eclipse, sunlight has to pass through the entire thickness of Earth's atmosphere at a grazing angle, essentially every sunrise and sunset on the planet, layered together and bent toward the moon. The blue light is almost entirely filtered out along the way. What survives, what makes it all the way around Earth's curve and across the 250,000 miles to the moon's surface, is mostly red and orange light. So the moon isn't glowing with its own light or reflecting a full white sun. It's bathed in the filtered, refracted leftovers of every twilight happening on Earth at once. You are, in a very real sense, watching the combined color of all the sunrises and sunsets on the planet projected onto the moon like a screen. This is exactly the same mechanism, incidentally, that makes the sky red during a smoky or dusty sunset, just scaled up and wrapped around an entire hemisphere. Astronomers even have a name for how vivid this red actually turns out, the Danjon scale, which rates the darkness and color of a lunar eclipse from 0, an almost invisible, blackish eclipse, to 4, a bright, coppery red one. What determines where an eclipse falls on that scale isn't something on the moon at all. It's what's happening in Earth's atmosphere at that moment. Volcanic eruptions, for instance, changed eclipse colors within recorded history. After Krakatoa's massive eruption in 1883, and after Mount Pinatubo in 1991, lunar eclipses observed in the following months appeared unusually dark, sometimes described as nearly disappearing, because volcanic ash and aerosols high in the stratosphere blocked and scattered even more sunlight than usual, preventing much of it from bending through to the moon. Cleaner air, by contrast, produces the classic bright, blood orange eclipses people expect. This detail turns lunar eclipses into something more than a beautiful coincidence. They are, in effect, a natural instrument for checking the health of Earth's atmosphere from 250,000 miles away. Scientists have used the brightness and color of past eclipses as indirect records of major volcanic events, essentially reading Earth's atmospheric turbidity off the face of the moon. A blood-red moon is really a message. It's Earth telling you what its air is doing, without a satellite, without a sensor, just ancient physics playing out at planetary scale. Widen the picture a bit more, and it gets stranger. Every particle of light landing on the moon during a total eclipse has essentially detoured through Earth's edge to get there. It's not moonlight reflecting sunlight in the ordinary sense at all. It's sunset light from thousands of sunsets happening simultaneously around the globe, bent by refraction, filtered by scattering, and delivered across space to paint the moon in shades of copper, rust, and deep red. And this isn't unique to Earth and its moon, either. Any planet with an atmosphere would cast a colored shadow onto its own moons during an eclipse, the exact hue depending on that atmosphere's composition. A world with a thick, dusty, or heavily colored atmosphere would project a very different tint entirely. So the next time the full moon dims and reddens, resist the instinct to think of it as going dark. It's doing the opposite, in a way. It's catching the last bent rays of every sunrise and sunset on Earth, all of them arriving at once, all of them turned red by the same air we breathe. What looks like an eclipse's shadow is really Earth's atmosphere signing its work across 250,000 miles of empty space. And if a thin envelope of gas, barely 100 kilometers thick, can reach out and color an entire moon, it leaves an open question worth sitting with. What other quiet signatures is our atmosphere leaving on the universe around us that we've simply never thought to look for?